In volume rendering, transfer functions play a crucial role in classifying structures of interest and assigning optical properties. However, designing these functions can be tedious and unintuitive. Traditional approaches, including interactive specification, are often slow and require model training. To address these limitations, the authors propose a novel method that leverages self-supervised pre-trained vision transformers to automatically select similar structures based on user annotations. Unlike traditional 1D and 2D transfer functions, which fail to extract semantically coherent regions and separate different structures that share a value range, the proposed method utilizes the feature extraction capabilities of vision transformers to identify remaining voxels of a structure using feature similarity. This approach computes a similarity map S, enabling quick inference and interactive exploration of the volume data without requiring model training. The authors acknowledge the challenges of utilizing self-supervised pre-trained vision transformers in the 3D domain, including extracting meaningful features from 3D volumetric data and combating low-resolution features. To overcome these challenges, they propose extracting features slice-wise along multiple axes, merging the resulting 2D features to a 3D feature volume, and using a refinement step that increases the resolution of the similarity maps and adapts to the underlying intensity volume. The proposed method enables an interactive workflow where users can explore volume structures through annotation. Once a structure of interest is fully discovered, users can enable a refinement step to increase the resolution and visual quality in 3D rendering. This approach offers a significant improvement over traditional methods, enabling faster and more intuitive transfer function design in volume rendering. The authors propose a novel approach to transfer function design in volume visualization, leveraging neural network features to select and visualize volume structures from a minimal number of annotations. This approach enables an interactive annotation-guided transfer function design process with instant feedback after each annotation. The authors utilize a frozen self-supervised vision transformer to extract robust and discriminative features from volume data, which serve as a basis for the annotation process. They also propose a merging scheme to combine the extracted 2D feature maps into a 3D feature volume. Furthermore, the authors introduce a 3D extension to the fast bilateral solver for refinement of the annotated similarity volumes. The source code for this approach is made publicly available. The authors provide an overview of related work in transfer function design, including approaches using different features, such as intensity, gradients, segmentation maps, and dimensionality reduction. They also discuss learning-assisted transfer functions, which employ machine learning methods during the design process, including approaches that collect annotations from users and train machine learning models to classify the acquired data. In contrast to prior work, the author's approach requires minimal annotation and no further training, leveraging the generalized feature extraction capabilities of self-supervised pre-trained models. This saves time and enables off-the-shelf application on a wide range of domains. The importance of semantically relevant structures in intermediate features is highlighted when pre-trained on unlabeled data. Masked image modeling approaches are discussed for their effectiveness in model fine-tuning. Various segmentation methods, including interactive approaches, cross-modal vision transformers, and the application of VITs to 2D and 3D medical image segmentation, are covered. The author's approach involves extracting a feature volume using a pre-trained Dino VIT, sampling features at user-annotated locations, and computing a similarity volume. The process is detailed, including the refinement of the similarity volume using a 3D bilateral solver. Feature extraction using VITs is emphasized to capture semantic meaning in the features. The feature extraction pre-processing step involves slicing the volume data along each axis and feeding it through a pre-trained Dino network, yielding a feature volume F. User annotations in a slice viewer are then used to compute similarity with the feature volume F, providing immediate feedback that enables the user to focus on regions missing after initial annotations. The attention mechanism in the Dino VIT computes the attention matrix A, determining the influence of values V for a specific attention head. The keys K of the last self-attention layer are saved as feature maps, representing semantic features designed to be matched to queries. The feature volume F is obtained by merging the feature maps along each principal axis, reducing dimensions by the patch size of the VIT, and then averaging to the target dimensions. The Dino-Witz-8 network is chosen for its ability to extract meaningful features without requiring specific training. The feature resolution may be low, but optional upsampling allows for control over the final dimensions. Computing similarity maps involves using the feature volume F to compare with user annotations, enabling the user to refine their annotations based on the similarity feedback. Once satisfied with the annotations, the bilateral solver can be enabled as a post-process to obtain super-resolution histology with increased resolution, typically taking less than a minute and repeated for each class. This innovative method for annotating structures within volumetric data leverages attention-based features to compute similarity between annotated voxels and feature voxels. This similarity computation guides the user in placing further annotations, ensuring a high level of accuracy. The approach involves generating a similarity map, which is subsequently refined through a post-processing step to enhance visual fidelity. The refined similarity map is then rendered, providing an intuitive annotation interface. This interface features tools for setting annotations, viewing similarity maps, and managing classes. The effectiveness of this approach is demonstrated through experiments, showcasing its ability to accurately annotate structures within volumetric data. The proposed approach is demonstrated through a comprehensive evaluation, including visual results, quantitative assessments, and a user study. An annotation interface, shown in Figure 2, allows users to set annotations using individual points or brushing, calculating the similarity map SL and displaying it alongside annotation positions. This process informs the user about areas requiring further annotations for accurate segmentation. The method is tested on various datasets and modalities, with visual comparisons provided in Figures 37. These results showcase the method's applicability on different types of data, including BONSAI, MRIHEART, TOOTH, VIS Contest 2010, and animal scans. The required number of annotations per class varies across datasets, ranging from 5 to 17. A quantitative evaluation is performed using the CTORG segmentation dataset, where the proposed approach is compared to related work, specifically the support vector machine, SVM, and random forests, RF, methods by Soundararajan and Schultz. The comparison is fair, as the re-implemented approaches utilize the same classifiers from scikit-learn. Notably, the proposed method achieves comparable results with 3 orders of magnitude fewer annotations. Additionally, the resolution of the extracted feature volume F is investigated, and a user study is conducted to assess the usability of the presented method. Further experiments are detailed in the appendix, including the maintenance of topological consistency using the 2D right-pointing arrow 3D merging strategy, combining Dino features with SVMs and RFs, and a quality assessment of the refinement step's ability to restore fine details lost in low-resolution similarity maps SL. The proposed method for generating transfer functions in volume rendering is compared to existing methods, such as SVM and RF approaches by Soundararajan et al. And SAM-MED 3D. Qualitative results are presented for various volume datasets, including Bonsai, Tooth, and MRI Heart, demonstrating the effectiveness of the proposed method in defining meaningful transfer functions from just a few annotations. A visual comparison with the CTORG dataset shows that the proposed method outperforms the SVM and RF approaches when using an average of 5.2 annotations per class. Quantitative comparisons on the same dataset confirm the superior performance of the proposed method in terms of precision, recall, F1 score, and intersection over union, IOU, for different classes. The impact of feature volume resolution on the proposed method is also discussed, with the ability to control the resolution of the feature volumes extracted from the VIT. This flexibility allows for a trade-off between computational efficiency and segmentation accuracy. The research paper presents a comprehensive analysis of the development and implementation of a novel algorithm designed to enhance the efficiency of data processing in real-time systems. This new approach, dubbed real-time data processor, leverages advanced mathematical concepts such as Fourier transforms and wavelet analysis to optimize data handling in time-critical applications. The paper begins by outlining the challenges inherent in traditional data processing methods, particularly those related to latency and computational overhead. It then delves into the theoretical underpinnings of the real-time data processor, detailing its reliance on signal processing techniques to decompose complex data sets into more manageable components. The authors also provide an in-depth examination of the algorithm's architecture, which consists of three primary stages: data input, processing, and output. Each stage is meticulously described, with special emphasis on the role of wavelet transforms in reducing noise and improving signal quality during the processing phase. The paper's central argument revolves around the potential for the real-time data processor to significantly reduce latency and enhance accuracy in data processing tasks, making it particularly suited for applications where real-time responses are paramount, such as financial trading platforms and autonomous vehicle systems. The authors further discuss the limitations of their approach, including the need for further refinement to accommodate large datasets and the requirement for specialized hardware to achieve optimal performance. They also propose avenues for future research, including the integration of machine learning techniques to improve predictive capabilities and the development of hybrid algorithms that combine elements of both Fourier and wavelet analysis. Ultimately, the paper concludes that the real-time data processor represents a promising step forward in the field of real-time data processing, offering a novel solution to long-standing challenges and paving the way for future innovations in this rapidly evolving field. The authors conduct a comprehensive comparison of their method with existing approaches, focusing on segmentation metrics, annotation amount, and computational efficiency. Their method achieves superior performance, with an accuracy of 0.981, precision of 0.989, recall of 0.990, F1 score of 0.990, and mean intersection over union, MIOU, of 0.981, outperforming SAM-MED 3D, random forests, and support vector machines. Notably, their approach requires only 5.2 annotations per class on average, achieving superior IOU compared to thousands of annotations required for SVMs and RFs, as illustrated in Figure 8. The authors also investigate the impact of feature volume resolution on unrefined similarity maps, demonstrating that higher feature resolutions provide less visual artifacts but do not significantly affect the final refined results, making the method practical for consumer GPUs. In terms of computational efficiency, the author's approach is highly efficient, extracting features once in the beginning and requiring no training. The inference time of their approach is independent of resolution, followed by a post-processing step that varies with resolution, as shown in Table 3. Furthermore, the authors conduct a user study with 12 participants to verify the usability of their approach. Participants with varying levels of familiarity with 3D software navigation were introduced to the user interface and asked to segment the lung, liver, and kidney, demonstrating the method's ease of use and effectiveness. The paper presents a comprehensive analysis of the usability and performance of a system designed for segmenting organs in CT scans. The results from a user study reveal strong segmentation outcomes, with high intersection over union, IOU, values and minimal annotation requirements. Participants achieved these results in a relatively short time, demonstrating the efficiency of the system. The System Usability Scale, SUS, score of 88.25 indicates above-average usability, suggesting that the system is user-friendly and effective. The graphical user interface is designed to facilitate ease of use, featuring tools for slice annotation and 3D rendering. This intuitive design enables users to navigate the system with ease, improving overall performance. However, the paper also highlights several limitations. For instance, the feature extraction process requires high memory requirements, which could be a challenge for systems with limited resources. Additionally, there is a potential for false detections due to similar intensities in CT scans, which may lead to inaccuracies in segmentation results. Future directions include the use of larger pre-trained transformers to enhance the system's capabilities and the option to retrieve higher resolution feature maps for more precise segmentation. These advancements could further improve the system's usability and performance, making it an even more valuable tool for researchers and clinicians working with CT scans. The paper presents a novel method for transfer function design in volume rendering, utilizing self-supervised pre-trained vision transformers. This approach enables users to create transfer functions for a structure of interest in seconds to minutes, reducing the need for a large number of annotations. The method can be extended through the use of newer and larger networks or networks that produce features queryable by natural language. Additionally, the paper proposes a 3D extension to the fast bilateral solver to upsample similarity maps to a high resolution, enhancing visual quality. The paper presents a comprehensive review of the current state-of-the-art in visual transformers for image segmentation tasks, focusing on their application in the medical imaging domain. It discusses various architectures and techniques used, such as the vision transformers, VIT, and SWIN transformers, which have been shown to outperform traditional convolutional neural networks in many image recognition tasks. The authors also explore the use of self-supervised learning methods, like masked image modeling and contrastive learning, to pre-train these models without requiring large amounts of labeled data. In addition, the paper highlights the importance of interactive segmentation methods, which allow for real-time adjustments during the segmentation process. These techniques are particularly useful in medical imaging, where accurate segmentation is crucial for diagnostic purposes. The authors emphasize the need for further research in this area, particularly in terms of improving the efficiency and usability of these models. The paper also provides an overview of several datasets and evaluation metrics commonly used in medical image segmentation tasks, including the CTORG dataset for multiple organ segmentation in computed tomography images. Furthermore, it discusses the role of visualization tools, such as InVivo, in facilitating the understanding and interpretation of complex segmentation results. The authors conclude by outlining potential future directions for research in this field, including the integration of multimodal data and the development of more efficient pre-training strategies. They also emphasize the importance of interdisciplinary collaboration between researchers from different fields to advance the state-of-the-art in visual transformers for image segmentation. The authors delve into the significance of the refinement step in segmentation-based transfer function design, focusing on its reliance on the initial low-resolution similarity map, SL. To explore this, they generate an incomplete similarity map with insufficient annotations, capturing only the central region of the liver in the CTORG dataset. The refinement step is then applied to this incomplete similarity map to determine if it can complete the structure and compensate for the lack of detection in SL. The results demonstrate that the refinement step effectively aligns low-resolution feature maps to the raw input, particularly at the borders of the structure, but it cannot complete structures far beyond what is detected in SL. If a structure is not sufficiently detected in SL, the refinement step is unable to complete it, resulting in block artifacts when rendered as an isosurface. These block artifacts are attributed to the sigma parameters of the bilateral solver, which control the window used for blurring. The authors conclude that the refinement step requires a sufficient detection of the full structure in the low-resolution similarity map to produce surfaces without artifacts, emphasizing the importance of both the initial similarities SL and the refinement step. The paper also addresses topological consistency in feature extraction, employing a 2D right-pointing arrow 3D merging strategy to achieve per voxel features that match similar structures throughout the whole volume. The authors investigate whether their merging strategy suffers from topological inconsistencies, creating two synthetic datasets, sphere and torus, at a resolution of 5123 to test this. The topological consistency of a 2D TO3D feature extraction strategy is evaluated, comparing it to slice-wise feature extraction. Figure 2 illustrates the results, where the slice-wise approach introduces topological inconsistencies, whereas the proposed merged feature approach preserves the topology of the sphere and torus. The bilateral solver can remove most block artifacts visible in both approaches. High-level global features extracted by the Dino network are used as input to support vector machines, SVM, and random forest, RF, classifiers. Unlike local features used in previous work, the Dino feature map contains more information. However, the SVM approach fails to make reasonable predictions, achieving low intersection over union, IOU, scores of 0.24 for the liver, 0.36 for the bones, and 0.0 for other classes in the CTORG dataset, resulting in a mean IOU of 0.09. The SVM is computationally expensive, requiring 407 seconds to fit and 2077 seconds to infer. In contrast, the random forest is faster to fit, 3 seconds, and infer, 2.5 seconds, but still fails to achieve meaningful segmentation, even with an increased number of estimators. Neither the SVM nor the RF surpass a training accuracy above chance. These results highlight the limitations of using SVM and RF with high-level global features and underscore the importance of the proposed 2D-3D feature extraction strategy, which preserves topological consistency and enables more accurate segmentation. Table 1 documents the annotation requirements for each class in the demonstrated datasets, ranging from 2 to 24 annotations per class. The datasets include bonsai, tooth, MRI heart, MRI brain, carp, and CTORG, with varying numbers of annotations required for each class. The author's approach leverages the 3D bilateral solver to increase the resolution of the segmentation and adapt coarse segmentations to exact borders in the raw input volume. This is crucial for segmenting fine structures that cannot be properly captured in the initial similarity map due to limited resolution. The bilateral solver restores fine details in the refinement step. Figure 4 presents a quality assessment of this process, comparing the author's segmentation approach with a carefully crafted 1D transfer function on the CARP dataset. The 1D transfer function serves as ground truth for the comparison, focusing on segmenting fine fish bones. The results show that the author's approach detects all fish bones accurately and avoids the noise present when using a 1D transfer function. The top row of Figure 4 displays the author's approach. The middle row shows the 1D transfer function, and the bottom row presents a comparison of two cross-sections of the fish bones. This evaluation highlights the effectiveness of the author's approach in capturing fine details in the segmentation process, demonstrating its ability to restore fine details and adapt to exact borders in the raw input volume. In the realm of 3D reconstruction, the visualization of fish bones has been a subject of interest for researchers. A comparative analysis between the proposed transfer function and the traditional 1D transfer function reveals distinct differences in their impact on this visualization. The proposed approach results in fish bones appearing slightly thicker, yet it maintains a close proximity to the actual bone locations, with most bones within 1 voxel distance. This comparison is visually represented through a table or graph, which underscores the effectiveness of the new transfer function in enhancing bone details without significant distortion. This advancement holds potential for more accurate representations and analyses in future studies. The segmentation of fine details is assessed using the 3D bilateral solver, as demonstrated on the CARP dataset. This approach effectively segments the top row's application to fine fish bones, revealing a comprehensive volume rendering through a 1D transfer function. The zoomed view on the right highlights the region marked orange in the top center, providing an in-depth analysis of the segmented area. The bottom row compares cross-sections of fine fish bones with planes marked teal and red. The intersection images show the border found by the 1DTF in green and the findings of our approach plus the 3D bilateral solver in blue, showcasing the precision and accuracy of the method.